Hey everyone. So in this next section, we're going to be talking about perceiving sounds and letters. And so we're going to cover a pretty wide range of different ideas and different topics. But first, I just want to get at some basic phenomena, some basic studies that have really provided some insight into how it is that we perceive either sounds or letters. And I will admit that there are already videos that demonstrate a lot of these better than I can talk about them myself, in part because of there being either very specific sound files that you need to hear in order to be able to understand them, or it's an influence between what you're hearing auditorily and also what you're seeing visually. And so one thing that I should point out to everybody is that on this slide, if you go into the PowerPoint for the slide, I provided links for the McGurk effect and also the phoneme restoration effect. We've already talked about speech segmentation, so I'll just briefly be reviewing that. But I just want to provide some oversight before we go through this slide. So basically, the McGurk effect, what it is it's an effect that was discovered where there's an interaction between what it is that we see when somebody's speaking and also what we hear. So again, I'll default to the link so that you can actually both experience the McGurk effect for yourself, but then also hear from one of the individuals who has done some research on the McGurk effect actually talk about it. But basically, the take-home message of the McGurk effect is that whenever we're in a room listening to somebody talk, we're not only taking in the auditory sounds of that person talking, but we're also looking at their mouth and taking information from what we're seeing about their mouth movements to help make sense of the sounds that we're hearing. So in the case of the McGurk effect, if you correctly play with both the phoneme that somebody is making with their mouth and also the sound or the phoneme that they're making from their vocal cords, then you'll actually hear something that was never actually presented, because that visual and auditory information influence each other in what it is that's perceived. For the phoneme restoration effect, we've already talked about this a little bit, and I've provided again a link so that you can experience yourself. But basically what ends up happening is, especially because most of the time we're listening to people in noisy environments, so you might have noises going on in your room. Again, Lewis has jumped up on the table and is making noises and shaking my microphone. And what ends up happening is that you may notice these noises, but you can still understand what it is that I'm saying, even if the phoneme, you might not hear the phoneme that I made. And the reason for that is because we're using top-down knowledge about what we know about speech, but also what we know about what people are talking about to fill in those gaps. So while we might not hear the exact phoneme, we can fill in that gap that the noise covered based on what we know about what are proper placements of words in speech, where certain words might go if somebody's talking, but then also we take into account what it is that somebody's talking about. So if I were to suddenly talk about, if I were talking and there was some confusion about a phoneme and whether I was talking about a principle in cognitive psychology or a car, then you would default to, oh, well, Dr. Miller must be talking about some concept in cognitive psychology. It would be weird for him to bring up a car reference in the middle of a lecture on perceiving sounds and letters. And so the phoneme restoration effect, please go to the link, check it out, but it really highlights our use of top-down knowledge, our knowledge about the world to help us perceive, especially in really noisy environments. We also talked about the problem of speech segmentation, right? And so just to remind people, this is the issue that whenever we're listening to a speech signal, we don't have any visual markers, but yet we're able to hear where one word starts and one word stops. And oftentimes, even if we were to have a visual representation, the sound wave of the sounds that somebody's making, a lot of times those gaps in the sound wave are actually in between words, and so we can't just use those gaps to help us split words. And so in the case of speech segmentation, again, we're using top-down knowledge. We're not using our knowledge about language, how language functions, and also the context of what people might be speaking about to help us break up the individual words in somebody's speech signal so that we can understand the sentences that they're saying. Now, the final idea that gives us some insight into how we perceive letters is something called the word superiority effect. And basically, in the word superiority effect, it's easier for us to identify letters when they're presented within a word. So here, we have an example of 3 potential trials that somebody might experience. In this first trial, they look at a fixation cross, is marked by this plus sign, and then they're going to see a letter pop up on the screen. In this case, that letter is going to be an E, and then a few seconds later, they're asked, did you see an E or a T, right? So they have to make some sort of a 2 alternative forced choice task here. And surprisingly, when people are presented with this particular scenario, they often don't recognize the letter. In fact, only about 60% of the time will they recognize the letter and correctly say, oh, the letter I saw was an E. Now, what's interesting is if we take the exact same experimental trial, we have a fixation point where people are looking at is marked by this plus sign. We present them with an E again, but this time that word E comes in at the end of the word plane. Then we ask them, did you see an E or a T? Then roughly about 80%, sometimes a little more, they're going to say, oh, I definitely saw an E. So that's the idea of the word superiority effect, that if that letter is placed within a word, people are going to be more likely to recognize, to remember, to identify that an E was presented to them. And they're also going to have faster reaction times for that. Now, what's kind of interesting, and I will say this number is probably a little unfair, it's a little low, but even if you put that letter at the end of a nonsense word, so I think we would all agree that there's no such word as clean, that people still show some benefit of that coming, or the E being presented in a, what we would call a pseudo word and not real world word, as opposed to if they were only presented independently with the letter E. And so there's still a word superiority effect, even for nonsense or pseudo words. As I said, that this basically falls in between if it was a real word, but this is the take-home message here is the idea that we're better at perceiving letters, at both recognizing them and also having faster reaction times to saying, yes, we did see them, when they're presented within a word as opposed to when they're just presented on their own as an individual letter. So, hopefully that helps to at least give some idea and some context for the how we perceive different sounds and letters. Now we're going to shift a little bit and talk about another characteristic of speech. And so this will actually cover the next 2 slides, but I want to set up some basic foundation before we go in and talk to specifically how we can categorize different speech sounds. And the first thing, or the way I want to start off doing this, is to talk to you about an idea called voice onset time, or VOT, V-O-T. And in the case of voice onset time, what we're interested in is the time or the amount of time between when your mouth starts a phoneme and when your vocal cords begin to vibrate. So the voice onset time is just that time between when your lips start to make the phoneme and when your vocal cords begin to vibrate. So to highlight this, I'm going to have you do a little activity as you're sitting next to your phone, next to your computer, and we're going to deal with 2 phonemes, pa and ba. And what I want you to do is I want you to take 2 fingers, and I want them to put them right near where your Adam's apple would be. And the idea here is that I want you to put your finger, it's going to vary a little from person to person, but I want them to put them on your neck, kind of in the middle of the neck where the Adam's apple roughly would be, so that you can start to feel your vocal cords. And if you do some talking, I'm doing this while I'm telling you to do it, if you do some talking, you should be able to feel your vocal cords vibrating. Now, what I'm going to do is I want you to say really slowly to yourself the phoneme pa. And so I'm going to do this with you here in a second. But as you're making the sound, or as you're producing the phoneme pa, what I want you to do is we're going to do it real slow, and I want you to focus on the amount of time between when your lips start to form the p sound and when you can feel the vibration of the ah in making the phoneme. And so again, we're going to do this really slow, but really pay attention to your lips and your vocal cords and the amount of time between when your lips start to make the sound and when you feel that sound in your vocal cords. So do this with me. Pa, pa. Okay, so one of the things that you should feel is there's a big amount of time between when you start making the p sound with your lips, and you feel your vocal cords vibrate. Now, again, when I say quote unquote a long amount of time, I'm doing this really, really slowly so that you actually can experience the time between that. And also, it's a relatively a lot of amount of time, but it's still pretty quick. Even if you're saying it slowly, such as there's a pretty quick amount of time. And so when we talk about voice onset times, we're talking about milliseconds. So to give you some perspective, milliseconds, there are 1,000 milliseconds in a second. So these are really, really small amounts of time. But in the case of making the phoneme pa, we have a really long voice onset. Now, I want you to do the same thing. Pay attention to your lips starting to make the sound ba, and also put your finger on your vocal cords and feel when your vocal cords vibrate. And so we'll do this together. Ba, ba, ba. Now, one of the things that you should realize as you're doing this is that there's a much shorter voice onset time between when your lips start saying the ba sound and you get the vibration of your vocal cords, right? And so this is an example of a really short voice onset time, where almost right after your lips start mouthing the b sound, that your vocal cords are going to begin vibrating. Okay, so that's the idea of voice onset time. Pa is an example of a long voice onset time. B is an example of a really short voice onset time. Now, often between certain phonemes, voice onset time is the only thing that's going to separate them. So the only thing that really differentiates, that separates ba from pa, is that voice onset time. The lip movements are very similar. And so it's really just the amount of time from when your lips start making the movement to your vocal cords beginning to vibrate that actually separate these two phonemes from each other. Now, I'm going to make another point here, but hopefully in the next slide that point should be a little bit clear. And that's that we're better at discriminating differences between different phonemes than we are within the same phoneme. So if we were to take pa and I were to record my voice into a recorder, what I could go in and do is by editing that sound file, I could change the voice onset time, right? I could cut chunks of that sound file out so that I had a really short voice onset time, or shorter onset time between a much shorter voice onset time while still making the same sound pa, right? And if I were to compare those two, the standard me making the sound pa and the shortened voice onset tone of pa, we would have a really hard time making telling the difference between them. And that's what I mean when I say that we have difficulty discriminating within a phoneme. So within the same phoneme, even if the voice onset time changes a little bit, we have difficulties identifying differences within the same phoneme. However, we are really good at differentiating the difference between pa and ba. And that's what I mean by between different phonemes. So that we are really good, even if we play with the voice onset time very, very carefully, we still have a pretty easy time being able to tell the difference between pa and ba. So keep those two things in mind. I'm going to switch to the next slide, and I'm going to come back to talking about this idea of ba and pa. But I really want to start off by talking about this graph. And if I start talking about this graph just by talking about ba and pa, oftentimes students get confused. So I'm going to switch things a little bit, and then I'm going to come back to ba and pa. So here I have some pictures that were taken from my office mate when I was in my postdoc. And so my office mate was working on fMRI studies, and so in the fMRI software, because you're basically taking pictures of people, you can go in and you can manipulate, and I'm using that term loosely, in that you can work on resolution and stuff like that. It wasn't like he was making up images of the brain, but you can manipulate different images. And one of the things that I was working on in my postdoc was there's this idea that you can measure people's dopamine. So remember, I'm interested in Parkinson's disease, and people with Parkinson's disease have lower levels of dopamine. And so I was wondering if there's some evidence to suggest that how many eye blinks somebody makes during a minute is indicative of how much dopamine is in the brain. So the idea being that they make fewer eye blinks if they have lower levels of dopamine, which would be awesome for me as a researcher, because the only other way to measure that is to use really expensive PET scanning. But if we could just come in and measure somebody's eye blinks, we could get some estimate of how much dopamine is actually in their brain. So as part of doing this study, what we did, and this is actually where this image comes from, is we would stare at a video camera for long periods of time and measure people's eye blinks. And so I had some undergraduate research assistants that were helping me with this project, and we were recording a bunch of people's faces and measuring their eye blinks, both people with Parkinson's disease and people without Parkinson's. And as part of that, what they would have to do is they'd have to stare at these movies of people staring at a camera and count their eye blinks. And one of the things that people notice, and it's probably fair, is that I look a lot like Grumpy Cat whenever I do this task. And so they were saying, oh, look, Dr. Miller looks just like Grumpy Cat. And so what my office mate did is he actually did a combined image. And so this is actually the 50-50 of combining me and Grumpy Cat together. And sadly, Grumpy Cat and I do look a lot alike, which is a little sad, but also kind of hilarious. So here we have a spectrum of me, 100% me on one side, 100% Grumpy Cat on the other, and then the spectrum could be varying degrees of Grumpy Cat myself. So for example, here it's 50-50, but it could be 75% me, 25% Grumpy Cat, or over on this side it could be 75 Grumpy Cat, 25% me. Okay, so here I'm just trying to represent the spectrum. Now, let's say that I was doing an experimental task where I wanted to get an idea of how people identified both me and Grumpy Cat. And so what I might do is I might present them with a bunch of pictures that are on the spectrum of me and Grumpy Cat and ask them to press a button to tell me, is that Grumpy Cat or is that me? And so we can think of, in this graph, we can think of this x-axis as being this Grumpy Cat to Dr. Miller spectrum, right? So over here at -25, that's 100% me. Positive 75 is 100% Grumpy Cat. And then we're presenting all of those different degrees of me and Grumpy Cat to participants and having them judge whether is that Dr. Miller or is that Grumpy Cat. Now, if we were to do that, then what you would expect is if this purple line were me, that when you showed a picture that was 100% me 100% of the time, people would say, yes, that's Dr. Miller. However, as we moved more towards the 50-50, Dr. Miller Grumpy Cat, you would expect about half the time they would say it's Dr. Miller. The other half of the time they would say it's Grumpy Cat, right? And so you get this smooth transition as we went through the spectrum where when it was me, a lot of people would say 100% of the time, oh, that's Dr. Miller. As we moved more in towards the, as we included more Grumpy Cat, you would expect that to drop down a little. People might say Grumpy Cat, but still 80% of the time they would say it's Dr. Miller. As we hit this 50-50 mark, about half of the time people would say it's Dr. Miller, half the time they would say it's Grumpy Cat. And then as we moved closer or further on this Grumpy Cat spectrum, especially over here, we would say roughly about 0% of the time people are going to say that it's Dr. Miller. So this purple line, this S-curve, or kind of backwards S-curve, is basically saying that people are accurately perceiving, as we add more Grumpy Cat to the Dr. Miller picture, that people are accurately identifying me as Dr. Miller. Now this orange line is just the responses of people that are saying Grumpy Cat. And you would expect that to be the opposite, right? If people are 100% of the time saying that's Dr. Miller, you would expect that the 0% of the time they're saying that it's Grumpy Cat. Expect the same thing at 50-50. And when it's 100% Grumpy Cat, you would expect that people would say Dr. Miller 0% of the time and 100% of the time Grumpy Cat, right? So here we have two almost redundant S-curves, right? We could just look at one of these S-curves, and if we know this is the S-curve for Dr. Miller, we can just automatically assume what the S-curve is for Grumpy Cat and vice versa. But we should have this smooth transition as we work through the Dr. Miller Grumpy Cat spectrum as we move from Dr. Miller to Grumpy Cat. So hopefully that makes sense. If people have questions, definitely feel free to ask those questions. I'm happy to answer them. I realize this is kind of a tough concept. But now let's go back to ba and pa. Okay, so here we have voice onsets. And remember that there's a really long voice onset for pa, pa, and so pa is being represented as this orange line, right? And so here at plus 75, where we have this long onset, the time between lip movement and me actually vibrating my vocal folds, that 100% of the time people are going to say it's pa. And what we would expect is the perception of the phonemes ba and pa should be similar to how people would perceive the differences between me and Grumpy Cat. That we should have these nice, smooth transitional curves between ba and pa. However, what we actually find is that that's not the case. That people do not perceive phonemes the same as they would perceive the differences between myself and Grumpy Cat. Instead of having a nice S-curve, basically what we have is a standard box here. So in this particular case, the purple line is representing, so I should say on the x-axis here, this is just voice onset time. So over on this side, it's going to be a ba sound. Over on this side, it's going to be a pa sound. So we're just changing voice onset time in between ba and pa till we can see where that crossover is. So in what we actually find here, we see that if we present anything in this range of voice onset times, remember the difference between the lips and the vocal cords being activated, if we present any voice onset times within this category, 100% of the time, people are going to say that that sound is a ba, right? And 0% of the time, they're going to say that it's a pa. So what we see when we look at pa is a very similar thing. There's a sudden drop-off where people will go from voice onset times where they're like, no, that's clearly a ba, that's clearly a ba. And then suddenly, within a relatively short amount of voice onset times, people will suddenly start saying, nope, that is definitely a pa, definitely a pa. And every voice onset change after that is definitely a pa. This box-like shape where we get these sudden transitions where 100% of the time people say that it's ba, and then over a relatively short degree of voice onset times they suddenly start saying that it's a pa, is something called categorical perception. And categorical perception is just a creation of distinct categories when typically there should be gradual changes along a continuum. Or to put that in other words, categorical perception, or these boxes, are basically saying, okay, anything within this voice onset time is categorically identified to us as a ba. Anything within these voice onset times is categorically perceived to us as a pa. So, when it comes to categorical perception, this does happen, but it's not always common, right? As we showed with the Dr. Miller or Grumpy Cat, that typically when we ask people to identify between a spectrum of two things, there's this kind of smooth transition that occurs over time. However, in categorical perception, there's not this smooth transition. And this is what happens for phonemes. So this box-like shape is letting us know that there's categorical perception and specifically that phonemes are categorically perceived. There is a range of voice onset times, and if something is within that range of voice onset times, it is going to fall into the category ba, or it's going to fall into the category pa. Now, remember back earlier when I said that it's easier for us to discriminate between two different phonemes than it is within a phoneme? This categorical perception is what I'm talking about. As you can see here, looking at the graph, it's very easy for us to discriminate between a ba and a pa, right? This categorical perception lets us see that it's super easy to tell the difference between a ba and a pa. However, remember that I said that within a category, it's not easy for us to tell the difference. And this is what we're seeing underneath of these individual boxes that are being presented for ba and pa. Within that pa category, it doesn't matter if we have a voice onset time over here versus over here. It's still going to be really tough for us to identify any difference between those pas. We're just categorically going to hear it as a pa. So hopefully that makes sense of what categorical perception is and why we say that phonemes are categorically perceived. Now, I do have a couple interesting things to say about this, because I want to tie it back to what does this actually mean about language and how children learn language. And the most important point to walk away with here is the fact that children need to be exposed to different phonemes in different languages at a relatively early age. And so this is why things like Sesame Street and other children's programming have really been trying to present students with exposure to a bunch of different phonemes. Because what happens is if children are exposed to phonemes at a relatively young age, approximately under 12, then what's going to happen is that they're going to develop these categorical boundaries or these categorical perceptions for the phonemes, right? So let's say that we have a child that's only exposed to the English language. By hearing English, they're going to start developing these categorical boundaries for the different phonemes that are made up in English. However, if you present them with phonemes from Spanish and they've never been exposed to Spanish, then they're actually going to perceive the world like this. They're just going to have a nice smooth transition between them. They're not going to have categorical boundaries between those phonemes. So categorical boundaries are really important because they're evidence of how it is that children learn language. And one of the big pieces of evidence here is that children need to develop these categorical boundaries for phonemes, whether it be just one language, multiple languages, but they need to develop these categorical boundaries in order to be fluent speakers of those languages later in life. And so this is why a lot of times different programming, schools, and whatnot are trying to expose children to different languages early on so they can develop these categorical boundaries and actually be better, more fluent speakers of different languages because they have these categorical boundaries of sound. Now, typically what happens is if somebody's not exposed to language, so for myself, I was only exposed to English as a young child. If you were to have me do a phoneme discrimination task with equivalent phonemes as pa and ba in Spanish, this is basically what my curves would look like. There would be a smooth transition. It was just the same as any other sort of perceptual stimuli. It would be the same as judging the difference between Dr. Miller and Grumpy Cat. I would just hear them as things changing on a continuum. I would not have these categorical boundaries. Now, one of the results of this is that whenever, if I'm trying to pronounce a Spanish word or something like that, that a lot of times I'll mispronounce that word because I not only don't have the categorical boundary for it, but I can't tell the differences between the different sounds. And so often, when we have problems hearing those differences between different sounds, that's evidence that we don't have a categorical boundary for those phonemes. So for example, when it comes to rolling R's, there are some differences in different ways that you can roll your R's. However, many of my Spanish-speaking friends that are trying to show me this and to teach me this, I can't hear any difference between them. Another example of this that's common in the case of Asian languages. In Asian languages, there's no phonemes that approximate the R and the L in English language. And so that's one of the reasons why a lot of Asian-speaking individuals who haven't been exposed to English tend to blur their R's and their L's, because to them, their R's and their L's are like this. They don't hear the differences between them. They don't have a categorical boundary. And because of that, to an English listener, it sounds like what they're perceiving as an R might actually be more of how we would categorize things as an L sound. So categorical perception is important. It really does kind of lay the foundation for helping children to learn different languages and also learn them well into a level of fluency. One of the things that you may have heard me too, and this is just kind of an interesting aside, is that people have led or have used this categorical perception to say, okay, well, clearly, if we have categorical perception for phonemes, then clearly that means that there's something about speech that makes it special. And there's this whole hypothesis, the speech is special hypothesis. And that speech is so important to humans, and because of that, we develop categorical boundaries for it. However, what's interesting is that we can also present chinchillas with phonemes of the English language, and they also will develop categorical boundaries for the different phonemes that make up English. So this argues against the speech is special idea, but it's also kind of interesting to the fact that we can actually, if presented at the right stage of life, for chinchillas can actually create categorical boundaries for phoneme perception for elements of the English language. So realize this is kind of a long video. We covered a lot here. Hopefully it makes sense. If you do have any questions, definitely reach out. Happy to answer your questions and answer any questions you might have about perceiving sounds and letters.